Section 8.4 is trigonometric substitutions, and this is one of my favorite topics in Cal 2 because it's something that I used to hate when I was a student, but I've learned to enjoy since I really understand it really well. And what this section is going to do is it's going to negate the need for us to memorize all of those integrals of the inverse trig functions. We're going to be able to integrate a lot of different types of problems using trigonometric substitutions, and it comes from right triangle trig. Okay, so if you'll recall from your trig functions, if we have a right angle right here, the side that's opposite that right angle is called the hypotenuse. These legs we're going to call, if this is our angle theta right here, this is the opposite side, and this would be the adjacent side. And I know this is very basic, but it all hinges on right triangle trig, so I'm going to go into a lot of detail today. So if I had an expression that had a radical in it, and it was the sum of two squares, I would want to set up a right triangle like this for my substitution. We know from trigonometry that opposite over adjacent is equal to tangent, right? And so we could say that x is equal to a times tan theta. Let me kind of explain why that works this way. I don't know why, but when I draw triangles, right triangles, I always draw them oriented this way. It's just easier for me to draw. So if we have side A, side B, and side C, we remember the Pythagorean Theorem that says a squared plus b squared is equal to c squared, isn't it? If I were to take the square root of both sides of this triangle, I would have the square root of a squared plus b squared is equal to the hypotenuse. So what I want you to notice is anytime you have the sum of two squares underneath a radical, that is going to be the hypotenuse. The radical is going to be the hypotenuse. And then the opposite side, we want to always let be x if at all possible. The adjacent side, we always want to be a number if at all possible. And that means that if I have the sum of two squares under a radical, that will always be the hypotenuse. And then if this is my angle theta right here, I'm going to have tan theta is equal to the opposite over adjacent. If I solve that equation for x, I would multiply both sides by a, and that's where this comes from. X is equal to a tan theta. Now over here I said if at all possible, we want this side to be the opposite side to be x, the adjacent side to be the constant, and the hypotenuse to be the radical. That's only possible if we have the sum of two squares. What if we have the difference of two squares, like in this triangle right here? Well, if I have the difference of two squares, whatever's listed first in the subtraction is going to be the hypotenuse. So if I had a, b, and c, if I wanted to solve this equation for a, I would start with the Pythagorean theorem, a squared plus b squared is equal to c squared. And if I want to solve for a, I would subtract b squared from both sides, and then a would be equal to the square root of c squared minus b squared. Whenever you have subtraction, whatever's listed first in the subtraction has got to be the hypotenuse. So here, the adjacent side I wanted to be down here at the bottom, but because the a is listed first, that a now has to be the hypotenuse. So the radical that was in the hypotenuse before gets swapped out on the position of what is now in the hypotenuse, and that's my adjacent side. And if I wanted to take this right triangle and solve it for b, I'd start with a squared plus b squared equals c squared. And if I solve it for b, I would get b squared is equal to c squared minus a squared. And so then I would take the square root of both sides and say that b is the square root of c squared minus a squared. So when this side right here, the x is listed first in subtraction underneath the radical, the x has to take the place of the hypotenuse, because whenever you're solving a quadratic equation for any one of these three sides, if you have subtraction under the radical, whatever term is listed first is going to be the hypotenuse. If you have addition, you're going to let the radical be the hypotenuse. If you have subtraction, whatever's listed first is going to be the hypotenuse, and then those two things will swap positions. So I said I always want my x to be the opposite side if it can be. Over here, x can be the opposite because what's listed first is a, which I wanted to be my adjacent. So a is now the hypotenuse, and the radical moves into a's position. Over here, when the x is listed first in subtraction, the x has to be the hypotenuse, and the radical then switches to x's position. If you can draw a right triangle to solve these problems or to do substitutions in these problems, you're going to be able to solve a whole bunch of different types of problems, and they're not going to be terribly difficult. So the procedure that you're going to go through for trigonometric substitution is first write down the substitution for x. Now the goal here is always to solve for x. So if this is how my triangle's written up, I want to get x by itself, so I want to look at x over a, where a is the constant, and so then that's opposite over adjacent would be tangent. Here I want to get the x by itself, and I always want to put x over a because it's simple. So that would be opposite over hypotenuse, and opposite over hypotenuse is sine, so x would be a sine theta. Here I want to solve for the x. That's the hypotenuse, and hypotenuse over adjacent would be secant, so I would get x is equal to a secant theta. We don't want to use the radical because we're trying to simplify things for our substitution. So what I would do in these situations is I would replace x with whatever the trig function is. That's why this is called trigonometric substitution, because we're replacing a variable with a trigonometric function. And the secret, or the key to being able to do this easily, is by drawing the right triangle to go with the problem. So we're going to write down a substitution for x and calculate the differential dx, and then specify the selected values of theta for the substitution. The key to this is drawing the right triangle. Will the problems work if you don't label your sides correctly on the triangle? Yeah, but it won't be as nice. It may be a more difficult problem. Once we solve for x, we find dx by taking the derivative of x. So we write x in terms of theta, and then that's going to give us a d theta to plug in place of the dx. We're going to substitute the trigonometric expression and the calculated differential into the integrand, and then simplify the results algebraically, and then we integrate the trig integral, keeping in mind the restrictions on the angle for the reversibility. Then we're going to draw an appropriate reference triangle to reverse substitution. I use the same triangle for both the substitution and the reverse substitution. So your first step is always going to be to draw a triangle. So in example 1, I notice I have sums between the terms underneath the radical. So when I draw my triangle here, because there's sums, I know that the radical will be the hypotenuse. So this is going to be the square root of 36 plus y squared. I said I always want the variable to be the opposite side, and I want the constant to be the adjacent side. So this is 6 squared plus y squared, which means the adjacent side to this triangle here is 6. There's my angle theta. Now I want to know what y is equal to. Well, if I do y over 6, that's opposite over adjacent, and that's going to be tangent theta. We know we have these right triangle properties from trigs that work, and so we're going to take advantage of those. So if I solve this equation for y, I'm going to get y equals 6 tan theta. And then my next step is to take the derivative of y. Well, that's going to give me dy equals 6, and the derivative of tangent is secant squared theta d theta. Don't forget your differentials. So in place of y, I'm going to plug in a 6 tan theta. In place of dy, I'm going to plug in a 6 secant squared theta d theta. But I don't have just a y here, I have this radical. Well, if I put that radical over 6, that's hypotenuse over adjacent. What trig function is hypotenuse over adjacent? Not cosine. Cosine is adjacent over hypotenuse. Hypotenuse over adjacent would be the reciprocal. That would be secant theta. And if I multiply both sides of this equation by 6, I get the square root of 36 plus y squared is equal to 6 times secant theta. What that means is that in place of this radical, I'm going to plug in a 6 secant theta. And in place of this dy, I'm going to plug in 6 secant squared theta d theta. This is all part of my substitution. So what I have now is that the integral of dy over the square root of 36 plus y squared is equal to the integral of 6 secant squared theta d theta. In place of the dy, I'm going to plug in the 6 secant squared theta d theta, and then in place of the radical, I'm going to plug in 6 secant theta. Now this integral doesn't look terribly difficult, because first of all, these 6's are going to cancel out, and this secant will cancel with one of those secants, and I'm left with the integral of secant theta d theta. And this is one that I said you needed to memorize because it comes up fairly often. The integral of secant theta d theta is equal to the natural log of secant theta plus tangent theta, and this would be plus c because I don't have bounds on my integral. Now, do you want to leave your answer like this in this form with the theta as the variable? No, you don't, because you did a substitution. Just like when we do a u substitution, we don't want to leave our final answer in terms of u. We want to go back to the original variable. When we do a trig substitution, we don't want to leave our answer in terms of the theta. We want to go back to the original variable, which in this case was a y. So we're going to use this same triangle over here to go back to our y's. So looking at the triangle, secant we said was hypotenuse over adjacent. So that's going to be the square root of 36 plus y squared over 6. And tangent we said is opposite over adjacent. So that's going to be y over 6. Notice we have a common denominator. So we can go ahead and combine these two terms. And that's going to give us the square root of 36 plus y squared plus y all over 6. Now on your test, I would accept this as an answer, but when you go to check your answer in the back of the book, it's probably not going to have that because we can use properties of logs to rewrite this and get rid of an arbitrary constant. Let that c absorb it. So do you remember the quotient rule for logs? Right, if you have the natural log of a quotient x over y, you could rewrite that as the natural log of x minus the natural log of y. So we're going to rewrite this problem using that quotient rule for logs, and this would be the natural log of the square root of 36 plus y squared plus y minus the natural log of 6 plus c. Now notice the natural log 6 is a constant, c is a constant, and we can combine those two terms into our arbitrary constant, and that would give us a final answer of the natural log of the square root of 36 plus y squared plus y plus some arbitrary constant c, and that would be our final answer. I would accept this on a test. That would be okay, but if you're checking your answer in the back of the book, this is probably the one that you're going to see. When you're working these problems, when you're done and you check your answer, if your answer can be algebraically manipulated into the answer that they have in the back of the book, then your answer would be fine for a test. All right, example 2. We're going to start by doing, well, we're not going to start by doing anything. I'm going to start by asking you, how do you recognize that this is a problem that's even eligible for the trig substitution? What do you notice in it that might indicate that it's a trig substitution problem? There's a fraction. It doesn't have to be a fraction, but there's a radical, and underneath the radical we have the difference of two squares. So if you have a radical with a difference of two squares, you can use a trig substitution. So I'm going to start by drawing my triangle. I'm going to put my angle theta right here, and this will be my 90-degree angle. Always start by answering what the hypotenuse is going to be. For this problem, what will the hypotenuse be? It would be 3 because we have subtraction. And remember, we said back here that whenever you're solving for any one of these variables, a, b, or c, if you have subtraction, the first number is always going to be the hypotenuse. So since I have subtraction right here, and this is 3 squared, that means the hypotenuse is going to be 3. Well, if the hypotenuse is 3, where is the radical going to go? Is it going to go on the opposite side, or is it going to go on the adjacent side? Adjacent. Why the adjacent side? Because we said that's where we wanted the number to be. But since it can't be there and the 3 went where our radical was but when we had addition, the radical now goes in the position of the 3, so that's going to be the square root of 9 minus x squared here, and this side would be x. Our next step is to solve for x so that we can find the differential and see what we're going to plug in place of x and dx and all that good stuff. So I need a trig function that will relate x to something else. So I need two sides. So I can either pick the hypotenuse or the adjacent side. Do I want to put x over the 3, or do I want to put x over the square root of 9 minus x squared? I want to put x over the 3 because if I use the radical, it would make the problem way more difficult. So I'm going to put x over 3 is equal to what trig function? That's opposite over hypotenuse. What trig function is that? That's sine theta. So when I solve this for x, that's going to give me x is equal to 3 sine theta. If I know x, I can figure out what dx is. dx is the derivative of x. The derivative of 3 sine theta is 3 cosine theta d theta. Your differentials become extremely important in these problems. So I'm going to definitely take off points if you're not writing your differentials. So I know what I'm going to plug in place of this dx. I need to figure out what I'm going to plug in place of that radical. Well, if I put the radical over 3, that's going to give me the square root of 9 minus x squared divided by 3. That's equal to adjacent over hypotenuse. What trig function is adjacent over hypotenuse? Cosine. So that would be equal to cosine theta. But I don't have the radical over 3, so I'm going to solve this for the radical. That gives me the square root of 9 minus x squared is equal to 3 cosine theta. On this problem, we have bounds. We need to change our bounds. These are the problems where you definitely want to change your bounds. So I'm going to come over here then, and I'm going to change my bounds. The question was, why do we have to change our bounds for these problems? If we don't change our bounds, we have to go back to the original variable in order to evaluate it. It's just as easy, if not easier, to change your bounds right now than it would be to do it after the problem. Because if I change my bounds now, I don't have to do this last step that I did here where I went back to the original variable. And I would like to avoid that, and since it's possible, it's easy to do. So the way we changed our bounds with u substitutions was we plugged in our bounds into x and solved for u, right? So what we're going to do here is we're going to plug in our bounds in place of x, and now we're going to solve for theta. So what I have is sine theta is equal to x over 3, and that means that if I take sine inverse of both sides of this, I get theta is equal to sine inverse x over 3. So let's find our lower bound first. Our lower bound is going to be equal to sine inverse 0 over 3 is 0. And sine inverse of 0 is 0. To get our upper bound, that's going to be sine inverse 3/2 divided by 3 is 1/2. And for what angle is sine equal to 1/2? That would be pi over 6. By the way, this is where knowing that little cheat chart, that cheat sheet table that I gave you for trig functions comes in handy. So what I may do is just grab that, copy it, and then drag it around with me so we can find those. So let me make one of those right quick. Okay, so I rearranged things so they'll fit on the screen a little better. So the reason that I knew that sine inverse of 1/2 was pi over 6 is because of this table that I showed you guys how to make. So we'd look at sine of is 1/2 when the angle is equal to pi over 6. That's the way we do this. So when I rewrite this problem now, I'm going to have the integral that goes from 0 to pi over 6 of, in place of dx, I'm going to plug in 3 cosine theta d theta. And in place of the radical, I'm going to plug in 3 cosine theta. And then we simplify this. The 3's are going to cancel out. The cosines are going to cancel out. And I'm left with the integral from 0 to pi over 6 of d theta. And what do we get when we integrate d theta? We get theta. And that's going to go from 0 to pi over 6. So using the fundamental theorem of calculus, we're going to plug in our upper bound minus plug in our lower bound, and that's going to give us our final answer of pi over 6. So the problem was easy once we changed the bounds. It wasn't terribly difficult. Looking at this problem at face value, before we did any substitutions, you might think, ooh, that looks hard. I don't think I'm going to be able to do it. You've got to get over that initial mental block of, oh, I can't do this. If you will follow the rules for the trig substitution, it's really not a bad problem. But the key to the problem is setting up your triangle correctly. Following the rules that I explained up here whenever we were manipulating the Pythagorean theorem. If you have subtraction under the radical, whatever's listed first has got to be the hypotenuse. So here A was listed first, so A is the hypotenuse. A normally I would want to be the adjacent side, so the radical and the A just swap positions. The X stayed the same. Here, when the X is listed first, the X has to be the hypotenuse, so the X and the radical swap positions, and this A stayed in the same position. This is kind of our starting point. And then all of these were either swapping positions with the radical in x like we did here, or the radical in a like we did here. And where that radical goes is determined by what's listed first in the subtraction. If it's addition, the radical's the hypotenuse. So let's look at another problem. How do y'all feel about this? So far, so good? It's a lot easier than anything we've done so far, and it makes sense while I'm sitting here guiding you. You won't know how easy or hard it is, though, until you practice it on your own. So that's why I encourage you to always do homework as quickly as possible after class. With example 3, we know we're going to have to set up a triangle, so I'm going to set that up here on the top. So this is going to be my angle theta, this is going to be my 90-degree angle, and what's going to be the hypotenuse? Notice that's always the first question I ask. What is the hypotenuse going to be? Because if it's addition, the hypotenuse is the radical. If there's subtraction, that tells us what the hypotenuse is. So for this problem, what is it? It is x. So where is the radical going to go? On the opposite side or on the adjacent side? The opposite. Remember, I said up here, let me go back. We always want the x to be over here as the opposite side if at all possible. The only time it's not possible is if x has to be the hypotenuse, and in that case the radical's on that side. So I keep going back to this picture. This is kind of like your Rosetta Stone for transcribing or translating these problems. Since x is the hypotenuse, the radical is going to go over here on the adjacent side, so that's going to be x squared minus 36. What is... Did I say adjacent side? I meant opposite side. Since x is the hypotenuse, the radical goes on the opposite side. And what is our adjacent side going to be? 6, not 36. It's the square root of that number. All right, so now I have to set up equations to solve for x. Well, if I do x over 6, that's hypotenuse over adjacent. What is x over 6 equal to in terms of a trig function? Hypotenuse over adjacent. Secant theta. So that means that x is going to be equal to 6 secant theta. What is dx equal to? The derivative of secant is secant tangent. So dx is going to be 6 secant theta tangent theta d theta. So I know what I can plug in for x. There's an x. I know what I can plug in for dx. There's a dx. The other piece that I have is the radical. If I want to know what the radical is equal to, I don't want to put it over the hypotenuse because that would give me another x. I want to put it over the constant. So that means that the radical over 6 is equal to what trig function? That's opposite over adjacent. That's tangent theta. So the radical by itself is going to be equal to 6 tan theta. So now it's just a matter of rewriting this problem. So I have the integral of, in place of dx, I'm going to plug in 6 secant theta tangent theta d theta. In place of x, I'm going to plug in 6 secant theta. Now that x is squared, so that means I've got to square this expression as well. And then in place of the radical, I'm going to plug in 6 tan theta. Now I do want to urge some caution here. When you're squaring this, you're squaring the 6 and the secant squared. So that's going to give us the integral of, I'm just going to write everything out, 6 secant theta tan theta d theta over, this is going to be 36 secant theta times secant theta times 6 times tan theta. Now I'm going to cancel. So these 6's are going to cancel out. This tangent is going to cancel out. This secant will cancel with that secant. And then what are we left with? We're left with 1 over 36, which is a constant that I can pull out. And then I've got d theta over secant theta. So that's 1 over secant theta d theta. Using your trig identities or your trig rules, what is 1 over secant theta equal to? Remember your reciprocal identities? It's cosine. So this is just 1/36 the integral of cosine theta d theta. Do you know how to integrate cosine? This is going to be sine theta plus c. 1 over 36 sine theta plus c. Do you want to leave this as your final answer? If you do, you'll get it wrong. We have to write our problem or our answer in terms of x because x was the variable of integration. What do I look at to write sine theta in terms of x? The triangle. So we know that when we have a right triangle, and this is the angle theta, sine theta is opposite over hypotenuse. So this is going to be 1 over 36 times, looking at the triangle, the opposite side is the square root of x squared minus 36 over the hypotenuse, which is x. So this would be the square root of x squared minus 36 over 36x plus c. That triangle's used twice. Once for solving for x in terms of a trig function, and then again when we do our back substitution and writing the trig function in terms of x. Now this looked like a horrible problem. The substitution wasn't that bad. The trig functions canceled nicely and gave us something that was easy to integrate. We just had to go back and write our answer in terms of x. Not a bad deal. Let's look at another one. Would you recognize that this problem was actually a trig substitution problem? Maybe, maybe not, right? Let me remind you of a property of exponents. If you have a raised to the m over n, that's equal to the nth root of a raised to the m, is it not? So this 3/2 power right here, how could I rewrite that? I could rewrite this problem as the integral from 0 to 5 square roots of 2 over 2 of 29x squared dx over the square root, because the denominator is 2, of 25 minus x squared cubed. And that makes solving this problem a trig substitution problem, because we've got a square root and we have the difference of two squares underneath the radical. So when I set up my triangle, there's my angle theta, there's my 90 degrees. What is the hypotenuse going to be? 5. So where is the radical going to go? Is it going to go on the opposite side or the adjacent side? Adjacent. Why the adjacent side? Because 5 we normally want it on the adjacent side, but because it had to be the hypotenuse, that's where the radical is going to go, where the 5 normally would go. So this is the square root of 25 minus x squared, and that means that this side then is going to be x. So using right triangle trig, I have x over 5 is opposite over hypotenuse. What trig function is that? Sine. You do have to know your trig, and if you need your trig formula sheet out during this part, that's fine. Eventually you're going to memorize it. So solving for x, we get x is equal to 5 sine theta, and then dx will be equal to 5 cosine theta d theta. The other piece that I need is the radical, and if I put that radical over 5, that's going to be adjacent over hypotenuse, and what trig function is that? Right, it's cosine. So the radical, 25 minus x squared, is going to be equal to 5 cosine theta. Eventually, I'm hoping you'll quit writing this step and quit writing this step and just go from here to here. It's okay if you still need to write this out so you can see, well, this is adjacent over hypotenuse and this is opposite over hypotenuse. Now notice also we have bounds on this problem. That means we need to change our bounds. Well, if x over 5 is sine theta, that means that theta is going to be sine inverse x over 5. So to get my lower bound, I'm looking at sine inverse. This is going to be 5 square roots of 2 over 2 divided by 5. The 5s are going to cancel out, and that gives us square root of 2 over 2. And what is sine inverse of square root 2 over 2? It's pi over 4. And then to get our upper bound, oops, that was our upper bound. I screwed that up. That was our upper bound. To get our lower bound, we're going to do sine inverse of 0, and sine inverse of 0 is 0. So now we're ready to rewrite this integral. So we have the integral from 0 to pi over 4 of 29. What am I going to plug in place of x? I plug in 5 sine theta from this right here. This came from our right triangle. Now that x is squared, so this is also going to be squared. And then what do I plug in place of dx? 5 cosine theta d theta. Very good. Over, that radical is going to be cubed, so that's going to be 5 cosine theta cubed. And now I'm going to clean up the arithmetic. So this is the integral from 0 to pi over 4 of, that's 29 times 5 squared is, let's just write it as 5 squared, sine squared times 5 cosine theta d theta over, that's going to be 5 cubed cosine cubed theta. And then we cancel where we can. So this 5 cubed cancels with that 5 square and that 5. And this cosine cancels with one of those cosines, leaving us a cosine squared. So that's going to give us, I'm going to go ahead and pull the 29 out now. And that's going to be the integral from 0 to pi over 4 of sine squared, ooh, I left off my theta up here, sine squared theta d theta over cosine squared. Well, what is sine squared over cosine squared? Tan squared, right? So I could write this as tangent squared theta d theta. Do we know how to integrate tangent squared? No, but what do I know how to integrate that's squared that goes with the tangent? Do you remember your Pythagorean identities? This is the Pythagorean identity. Tangent squared theta plus 1 is equal to secant squared theta. So what is tan squared theta equal to? Secant squared theta minus 1. So that means that I could rewrite my integral as 29 times the integral from 0 to pi over 4 of 1 minus secant squared theta d theta. And that's going to be 29 times theta minus, what's the integral of secant squared? It's tan theta from 0 to pi over 4. Now we just apply the fundamental theorem of calculus, and that means we're going to plug in our upper bound, which is going to give us pi over 4 minus tangent of pi over 4, minus, and then we plug in our lower bound, 0 minus tan 0. And we know that tangent is sine over cosine, so looking at this table over here, tangent of pi over 4 would be square root of 2 over 2 divided by the square root of 2 over 2, and that is going to be 1. And tangent of 0 would be sine 0 over cosine 0. 0 divided by 1 is 0. So those terms are going to 0. So that's going to give us 29 times pi over 4 minus 1. And you could leave your answer like that or get a common denominator and say that this is 29 times pi minus 4 all over 4 if you want. You can get a common denominator by multiplying 1 by 4 over 4. And that would be your final answer. You may see this written in the back of the book. You may see this. I just wanted you to be aware of how to do both of them. I think this is our last example. It looks like it is. Would you recognize that this is a trig substitution problem? You don't see the radical, do you? No, but couldn't I say that I could rewrite the square root of x squared is x, or I could say the square root of x squared is x. Couldn't I do that? So I could take this, using that concept, I could rewrite this as the square root of 13x squared plus 1 squared is equal to 13x squared plus 1. Let me do this. If I square that, isn't that what that's equal to? Squaring the square root just removes the radical and you're left with this over here, aren't you? I need to put that in parentheses though. So I could replace this with this, but that's squared, so that means I'm going to have to square this. What that means is I can rewrite this problem as the integral of 26 dx over the square root of the quantity 13x squared plus 1 raised to the 4th power. Do you see why this is raised to the 4th power? You say, well, it was squared there. Yeah, when it was written like that, it was squared. But when I rewrite that as a radical, I got to square that, and you square a square, you get a 4th power. Do the exponents make sense? Okay, because if they don't, then there's no point moving on. I wrote it like that because that makes it easier to see how you're going to set up your triangle for your substitution. So here's my right triangle. This is my angle theta. That's the 90-degree angle. What is my hypotenuse going to be? Now I have addition between the squares. So what's the hypotenuse going to be? The radical. It's going to be that entire radical expression. I'm just going to write 169x squared plus 1. So what is this opposite side going to be? 13x. And what is this adjacent side going to be? 1. So now I need to solve for x. So if I do 13x over 1, that gives me 13x is equal to opposite over adjacent is tan theta. So x is going to be 1/13 tan theta. What is dx going to be? It's 1/13 secant squared theta d theta. And so what is the radical going to be? Well, hypotenuse over adjacent gives me the radical. Hypotenuse over adjacent is secant theta. So using the substitutions from this triangle, that means that I can rewrite this problem as 26, oops, forgot my integral. The integral of 26 in place of dx, I'm going to have 1/13 secant squared theta d theta over that radical is secant theta, and that's raised to the 4th power, so I'm just going to write secant to the 4th. And that secant to the 4th I could write as secant squared times secant squared, and then one of those secant squares would cancel out. But let's go ahead and cancel. 13 goes into 26 2 times. This secant square cancels with 2 of those secant squares, and that's going to leave us the integral, well, let me pull the constant out, is 2 times the integral of 1 over secant squared theta d theta, because everything else from the numerator is gone. And what is 1 over secant squared? Cosine squared theta d theta. How did we handle integrating cosine squares? What did we have to do? What formula did we use? We had to use the power reducing formula for cosine. So that's what we're going to do here. So that's going to give me 2 times the integral of 1/2 times 1 minus cosine 2 theta d theta. Moving on, so this 2 times a half is going to cancel out, and that's going to give us 1. So that's just going to be the integral of 1 minus cosine 2 theta d theta. When I integrate 1, I'm going to get theta minus, and then cosine of 2 theta, when I integrate that, that's going to give me 1/2 sine 2 theta plus c. Well, now we have a problem because this triangle uses the angle theta, not the double angle 2 theta. What can we do to change this sine 2 theta into a theta? If you're changing an angle on a trig function, you have to use trig rules. So we have to use the double angle formula for cosine. Not for cosine, we have to use the double angle formula for sine. And sine 2 theta is going to be equal to 2 sine theta cosine theta. So that means that this is going to be equal to 1/2 times 2 sine theta cosine theta plus c. Well, the 2's and the halves are going to cancel each other out, and that's going to give us theta minus sine theta cosine theta plus c. Do I want to leave this as my final answer? No, I don't. I got to use the triangle to go back to the original variable. The original variable here was x. So I need to figure out, well, what is theta going to be? Well, I have this right here. 13x is equal to tangent theta. How could I get that theta by itself? Take tan inverse of both sides. So that means that theta is now going to be tan inverse 13x. And what is sine theta going to be? Well, sine is opposite over hypotenuse, so that's going to be 13x over the square root of 169x squared plus 1 times cosine, and cosine is adjacent over the square root of 169x squared plus 1. And so that means that my final answer is going to be tan inverse 13x minus 13x over 169x squared plus 1 plus c. Okay, the question was, how did I get the tan inverse? I'm going to give you the answer. Using this right here. I'm going to come down here. We have 13x equals tan theta. How I got theta by itself was I took tan inverse of both sides of this equation. And when you compose a function with its inverse, you get out what you put in. That would be the theta. And that's why I said theta was equal to tan inverse x. So this theta right here got replaced with tan inverse 13x. And this would be our final answer. Now here, the reason that I got rid of the radical was because I multiplied it by itself. Well, that's squaring a square root. That undoes the square root. I'm just left with the radicand. And then 13x times 1, I'm just using properties of multiplying fractions together. Multiply numerator times numerator, denominator times denominator, and this is what you end up with. Some of the problems can get a little more involved, but if you understand the process, you should be able to do the problems. The main thing with the problems in this section is don't get scared. If you set up your triangle one way and it makes the problem infinitely more difficult, odds are you set up your triangle wrong. Go back. Let's recap right quick what we did to set up the triangles. If I have addition between the terms underneath the radical, the hypotenuse will always be the radical. I always want the adjacent side to be the constant, the opposite side to be the x, if at all possible. The only time it would not be possible is if I have subtraction, in which case whatever's listed first under the subtraction and the radical is going to be the hypotenuse. Since A here has to be the hypotenuse, that radical moves into what I wanted to be the position for A. Over here, since x has to be the hypotenuse, the radical took x's position, the opposite side, and A got to stay down here on the adjacent side where I wanted it. Notice, anytime the radical is anywhere other than the hypotenuse, it's going to take the position of whatever came first under the subtraction out of the A and the x. You will get good with this with practice, I promise. These should be some of the easiest problems you do in this chapter. So you should be excited to do lots of homework for this section because it's going to make sense and be easy. Assuming you did section 8.3 homework, which was practicing the integrals with trig functions. Because what they're doing is they're taking these algebraic expressions when you do a trig substitution and you change them into trigonometric integrals. That's why it's important to do 8.3 homework first. So that wraps up section 8.4.